technology for environmental retrofitting, as hydrodynamic optimization and also other technological solutions like scrubbers or LNG retrofitting. Scrubbers, LNG, and also the ballast water convention, triggering some retrofitting works. So the goal of this presentation is to introduce the audience to the overall process of retrofitting, particularly ships in operation, in order to meet the environmental or operational challenges. Either retrofitting is triggered by imposed regulations or operational needs. It is a very demanding task which has many uncertainties. The first part of the presentation focuses on the general decision-making process of retrofitting, while the latter part focuses on the environmental and regulatory framework and also the existing technologies for this. Shipping is commonly believed to be the most energy efficiency mode in transport. However, there is societal pressure nowadays to reduce the environmental impact from shipping and also increase its sustainability. For this reason, the IMO has developed a package of measures aimed at reducing CO2 from emissions from shipping, and there is also an agreed timetable adoption for it. The specific measures are the EDI index, Energy Efficiency Design Index, for the design of new ships, and also the SEM, Ship Energy Efficiency Management Plan, for the operational phase. Among with other regulations, of course, existing in the amendments of MARPOL, that concerning the impact of shipping on the ocean and its species. For example, the ballast water treatment installation or the ballast water exchange management plan that should be on board ships. About 3/4 of vessels are rather young. At the moment, about 15 years old. So most ships in operation need solutions to reduce their pollution by retrofitting or other suitable measures. Incentives for retrofitting do not also come from regulatory pressure, but also from higher oil prices and the reduction of oil consumption achieved through slow steaming or other measures subject to changes on the ship. Well, during the design phase of a new vessel, and especially on the initial design, where there is a lot of freedom for design decisions, we have very little limitations. Maybe we have a principal dimensions fixed. However, even if we have some other constraints, we have a lot of flexibility, and the main dimensions are mainly constrained by the cargo capacity of the vessel. Within these constraints, during the initial design, the shape of the vessel's hull can be freely changed in order to optimize the geometry for performance and hence fuel consumption later on in the operation. So typically we have the forebody, which is modified during the design phase to actually optimized through loop of regulations in order to reduce the wave resistance, while the aft body shape is tuned for a low viscous resistance, high propulsive efficiency, and also homogeneous wake distribution. In this initial phase, the simulation-driven design, which is widely applied nowadays, can be effectively employed and also increase the knowledge about the system and also converge to a better solution in the shortest time. This is also displayed in the graph you can see here, where we have we can see that the time in design process, while the time progresses, the freedom actually of the designer reduces, and however at the same time the knowledge increases, and this knowledge gain that is coming from the simulation-driven design can give us a substantial time savings. However, in the terms of retrofitting ships in operation, the situation is very different. There are many constraints, and it's very difficult to optimize the vessel due to many fixed dimensions and properties of the ship. For retrofitting the ships in operation, there is a high number of constraints, namely the geometry, the actual different space in the vessel, which are already existing. There are, of course, regulatory it is already in operation and is already approved by the regulatory bodies, like state and the class societies. So this would mean that there will need to be additional work for compliance. Of course, there is also the constraint of cost. When you have already a ship in operation and undertaking a cost to retrofit, sometimes it's not something that operators would want to have. And further to that, there are also some collateral implications and also uncertainties that can arise while the retrofitting task is underway. So retrofitting for the existing ships is a task that is highly complex, and it needs a multi-objective optimization in order to reach a balance between constraints, design variables, and objectives. As you can see in the picture, there's a design of a passenger hull, for example, and you can see that in the red line along the longitudinal length of the ship denotes the frame spacing of the ship. This is one constraint for an existing ship, so the framing and everything is there, so you have to take this into account as a constraint. You also see a bounding box around the vessel, which denotes that the principal dimensions are there, and they cannot be, if they change, there will be, of course, implications. With the blue line in the vertical extent, you can see the deck heights of the existing vessel. So this is also an implication. This is also a constraint that needs to be taken into account. And with the blue plane, you can see the actual draft of the vessel, which is also something fixed for an existing ship. So all these principal numbers and dimensions are there, and retrofitting should take account for those and find solutions that won't have implication to the general particulars, and also to the regulatory framework that the original vessel complies with. Which are the triggers now for retrofitting of ships? The decision of retrofitting can be either voluntary or compulsory. So voluntary action is coming from the need to enhance, from the need of an operator to enhance its operational productivity, enhance the ship's fuel efficiency, probably improve the asset price of the ship, and maybe meet new trading needs or the charterers demand, and also sometimes from the societal pressure to have more energy efficiency and eco-friendly vessels. The voluntary retrofitting is seeking very specific benefits, intentionally by the owners in order to see a short return on investment. While on the other hand, there's the compulsory action, compulsory retrofitting, which is coming mainly from the regulatory framework, which is imposed upon the operators in order to enforce, for example, environmental regulations, and this is taken forward mainly by the United Nations under IMO, the European Commission, and from governments around the world. So in this compulsory action, most of the operators are looking for compliance with the regulations, and they want simply to implement the rules. So sometimes they're not looking for specific benefits that they can take this retrofitting, but it would be better if they would try to combine those two actions in order to meet the regulatory framework and at the same time seek for more efficiency.
Τώρα ναι, δεν βλέπω, να το ανεβάσω. Με το ελεύθερο γίνεται, γιατί είναι αυτό το πολλά. Ένα.
Yeah. Hello. Can you hear me? Can you hear me well?
What about the voice? Can you hear us as well?
Can you hear us? So actually, back to this slide again. So we said that the triggers for retrofitting of ships can be divided in two parts. We have the voluntary or the compulsory. So the voluntary actions are actually coming from the need of the operators to enhance first the operational productivity and then the fuel efficiency of their vessels, possibly to increase the asset price, uh, maybe to meet new trading needs or charter demands, and even sometimes by the societal pressure um, in order to have more eco-friendly vessels. For the voluntary retrofitting, operators are seeking very specific benefits and they are looking forward to short return on investment. On the other hand, there's the compulsory action, compulsory retrofitting, which is coming from the regulatory framework, which is imposed on them uh, mainly by nowadays mainly by environmental regulations, taking through by IMO, the European Commissions or other governments. So this means that in the compulsory retrofitting, owners sometimes they're looking only for the compliance and the simple implementation of the rules, while it will be more wise for them to combine both benefits of voluntary and compulsory actions, meaning that out of compliance they can also get some improvement in the efficiency of the operations. So nowadays the main retrofitting triggers, which are let's say compulsory, are coming from the amendments of MARPOL Convention and mainly from these six annexes described here. So the prevention of oil pollution, the control of noxious liquid substances, then we have the prevention from harmful substances and pollution by sewage from ships, the pollution by garbage, and lastly, and maybe more importantly for the latest regulations, the prevention for air pollution from ships. So what is put forward from MARPOL Annex 6 is the minimization of SOx SOx emissions and from the operation of ships. And also this takes care of NOx emissions and the CO2 emissions. So the aim of the IMO and the global community is to reduce the percentage of emissions from ships operations worldwide. In the picture here, you can see the global pattern of CO2 CO2 and SOx emissions relevant to the ship trading routes. And you can see that mostly in developing countries, developed countries, this is more substantial, and there is a high rate of emissions coming from dense traffic of maritime transport. Until 2010, there was a requirement for the SOx emissions to be below 1% in ACA regions. So this means in regions that they are especially controlled for emissions. While now is coming for 2015 a new margin, and the SOx emissions should be below 0.1% in ACA regions. And then we have a next level coming in 2020, which may also be applied globally, and there are at the moment doubts if it's going to be in 2020 or later on. This is of course the SOx control emissions are for all ships. However, there is also for new building vessels the control of NOx emissions, and there is different tiers. Now we are in the tier 1 has passed, and now we are in tier 2. Um, Tier 2 is a global regime, and then we're going to tier 3 by 2016, which is available for ecoregions only. So now, which are the ecoregions and which are the expected ecoregions in the future? So with the dark blue, you can see the existing ecoregions, which is of course in the Baltic area and also in the North Sea. And then on the other side of the Atlantic is the coast of North America, and also the other coast of North America. Uh, However, there are some possible future ECAs which will of course take some time to be developed, and we are not sure yet about the actual time where these regions will be declared as ECAs. So one possibility is of course the Mediterranean Sea, and there is doubt on whether it will be a unified ecoregion, or it will start with some smaller sub-regions and then develop further. For example, starting from the Adriatic Sea or some other specific region. So other ECAs maybe are also um, estimated, maybe in Japan or in Singapore, or in the northern part of Norway, or even in the southern part of the United States. Mm. 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 Yeah, that's good. Okay. So the development of course, the development of new ECA areas will be more substantial trigger for retrofitting actually even more ships, and making it even harder for older vessels to comply, leading to a new possibly into a new cycle of shipbuilding activity in the next decades. So some technical measures incorporated in regulations. Of course, is mainly through MARPOL Annex 6. It's the EEDI, the energy, as we mentioned before. Maybe, okay. So as we mentioned before, is the EEDI coming through MARPOL Annex 6, the Energy Efficiency Design Index, which applies to new ships built after January of 2013. However, this index excludes RoRo vessels, RoPax vessels, tugs, or offshore supply vessels, and some other specialized ships. Also, there are some gaps into the regulation regarding hybrid propulsion technology and diesel-electric propulsion technology, which will be probably clarified later on. So further to the EEDI, we have another technical measure, which is the Ship Energy Efficiency Management Plan. It is actually a plan for ships in operation, which is compulsory for all ships to carry on board, and need actually to monitor the energy efficiency of their ships and take actions in order to improve that. The main reason for implementing SEMP is to actually um, um, is to actually make the operators uh, take make the operators monitor the efficiency of their vessels and also educate the crew of their vessels in order to know what the operational efficiency and energy efficiency means. Let's say more technical measures that exist within the SEMP plan is the EOI index, which is the energy efficiency operational index, and it is also let's say an index which shows the efficiency of the energy efficiency of carried quantity um, over the distance of the vessel of the vessel. So, however, this EOI index is at the moment voluntary, and ship owners are only encouraged to use it in conjunction with their SEMP plan. These technical measures are put forward through various guidelines that they are proposed. They are proposed with they are proposed through guidelines through the IMO and specific resolutions. So we have the 2012 guidelines on the method of calculations of the EEDI for new ships. Then we had the development of the Ship Energy Efficiency Management Plan, and we have some guidelines on the survey and the certification of the Energy Efficiency Design Index. And lastly, we have the guidelines for calculating reference lines with regards to EEDI. At the moment, most ships they're starting okay. So to continue, most of the ships in operation at the moment they are starting to comply with the SEMP requirement. So they have developed plans and they are carrying them on board. However, as this was, let's say, a compulsory action as we defined before, most of the operators are doing this without gaining any benefit and simply by implementing the regulation. However, there are also more sophisticated operators that are trying to make the best out of using the SEMP regulation and also using the voluntary EOI index in order to monitor their operational efficiency. Also, there are now a lot of ships built under the EEDI calculation, and there are new standards at the moment being developed for the actual certification of ships with the EEDI and the actual sea trials in order to verify the EEDI power line references. However, there is growing concern in the industry about the EEDI regulation and the possibility of having underpowered vessels in order to comply with the regulatory framework. So there is continuous research upon that in order to see what will be proposed for the future. So retrofitting options to meet these SOx limits imposed by regulations. Firstly, we have the LNG as a fuel. We have using of marine gas oil. No. Okay. So what are the differences between those three options? Firstly, we have the LNG fuel. Okay. Okay. So firstly, LNG as a fuel. We said that there is, according to studies and prospects from manufacturers and shipbuilders and also designers, that there is a significant retrofitting cost coming with the use of LNG as a fuel. However, there is the importance of LNG fuel being at a lower price at the moment than heavy fuel oil, and is also expected to remain lower than HFO in the future. And however, there is an uncertainty about the spread between the LNG and the low sulfur fuel and also the heavy fuel oil, and we are not sure about the prices in the future. The second solution, use of marine gas oil. The best advantage by that is that it is actually the do-nothing scenario, because you don't need to change anything or retrofit your vessel for that. Maybe some modifications for the pumping booster pumping system of supply of fuel, or maybe some very minor modifications in the delivery of the fuel to the system. However, there is a very big disadvantage of using marine gas oil, because it comes at a higher price than heavy fuel oil, and much higher price than course, and there is certainly also an uncertainty on how the prices will be shaped in the future. And lastly, the use of scrubbers. Scrubbers, similarly as to LNG fuel, they have a significant retrofitting cost. So with the scrubbers, at the same time you use the heavy fuel oil, and you don't need to change the use of oil of fuel oil, and this also has an uncertainty about what will be the price of the heavy fuel oil. So you don't have any possible, let's say, expected return on your investment because you keep on using the same oil. Whether with LNG retrofit, you might expect some substantial gains in the future if the price remains low. So what are the problems with retrofitting and things that will be taken into account of ships? Firstly, in the retrofit, let's say more or less for the retrofit. At the moment, there is lack of liquidity for the operators, and there is no financial, let's say, stability, and also there is no financial incentives from banks to support retrofitting to meet this regulatory framework. Also, there are a lot of pending technical issues for all kinds of retrofitting, LNG, for scrubbers, and also there are also some very minor questions about the use of MGO sometimes in some ships. Now for the operation, there is a spread uncertainty about the operation procedures for when retrofitting such systems on board ships, and it's also a very important thing. It's the lack of trained seafarers to work with such new technology systems that they have not worked before. So various retrofitting technologies, as we can see here in the graph, and also the cost per ton of CO2 averted. You can see in the y-axis. So we have, for example, the monitoring of the hull condition. Then we have weather routing or use of different propulsors, monitoring the propeller condition, possibly the use of frequency converters in order to have a more efficient use of electrical motors. Trim optimization is one of the very good, let's say, good ways of having a good return on investment, and also speed reduction, which is, of course, done very widely nowadays. So on the other hand, we have other measures that can be much more intensive in terms of cost. So let's say gas fuel, that we said before, and then using of fuel cells, of wings, or waste heat recovery for exhaust boilers, or cold ironing, which is some parts that actually depend very much on the state of the technology, or even in the infrastructures available for each ship. So the market of retrofitting, it is expected to have a major uptake during the next years, and this is due to the regulations that are imposed, and for the actually compulsory retrofitting that most of the owners need to do. So if we see that the requirements of the IMO, they're coming for the potential type of ships that need to be retrofitted are ships above 400 gross tonnage, and they are ships that are constructed before 2005, and of course they're also for oil tankers constructed before 1996. Passenger ships are counted, and also ships constructed to carry ballast water before 2009. So this leads us to the table below, where we can see that how substantial the numbers are in terms of ships that will need retrofitting in the near future, and we end up with a number of about 30,000 ships that will probably need to be retrofitted in the very near future due to the IMO upcoming regulations. Some insight on retrofitting technologies. For example, here we have a screenshot of a work on optimizing the bulb of existing vessel. So as you can see here, it's evident that we need to take into account, as we said earlier, the main constraints of the vessel. So
you can see in the picture that the main vessel is kept intact, and we need to optimize for a bulbous bow that will fit into this existing vessel to existing dimensions. And this is done by an automatic optimization process that is actually it is meant to optimize for the wave resistance, for the bulb wave resistance. And we can see here in the graph a trend of as the bulb volume increases through the optimization, that the wave resistance decreases. And this gives us the opportunity to select through a big crowd of variants the best, the optimal design in order to retrofit our vessel. So this is one of the, let's say, state-of-the-art latest technologies used in optimization and mainly hydrodynamic optimization of existing ships in order to enhance their fuel efficiency. Moving on with hydrodynamic optimization, there are various possibilities and also various ways to enhance the fuel efficiency by using, let's say, efficiency devices in the aft part of the vessel, like after the propeller, like this, the Memphis duct or the or other kind of ducts that improve the wake field of the vessel. Also retrofitting, for example, the skeg of the lower part of the vessel in order to improve the flow to the propellers. And of course, after doing that in a simulation-driven environment, it can give you the benefit of creating a big number of variants and actually using the most optimal one. And this can, of course, be benchmarked by the EOI index that is you can see here in the picture, which also describes the composition of the EOI, having on the upper part the fuel times the CO2 emissions, the CO2 actual quantity within this fuel, divided by the cargo quantity carried by the vessel times the distance the vessel has traveled. And this gives us the actual operational efficiency index. Now we move on to retrofitting with scrubbers. Scrubbers have been used for a long time in the land-based industry, and they're more or less compulsory for big factories mainly in Europe and America. However, now they've gaining some part in the shipping industry due to the need of reducing the SOx emissions. So scrubbers mainly are used on the exhaust of the ships, and so let's say that fuel emissions are passing through the scrubbers, and the SOx elements are in a way neutralized in order to, and their percentage drops to the required one. So there are different type of scrubbers. There are the open loop scrubbers, the closed loop scrubbers, and also hybrid scrubbers. The open loop scrubber use water, and also they use a catalyst, and then they need to discharge actually the water. While closed loop use mainly fresh water, and they keep it in a closed loop discharge. And there's some hybrid methods at the moment, and also some other methods that are still under development. However, the scrubber industry in the maritime is not very mature yet, and we expect to see big improvements in the future of this technology. However, retrofitting with scrubbers is a costly job, and it's very demanding. you need to account for a new fuel funnel layout. You need to account for scrubber installation. Auxiliary machinery need to be put within the same scrubber, so you have multiple exhaust scrubbers needed, and there is also piping work to connect those. Also, there is a need of installation of new tanks to mainly a circulating tank for either the open or the closed loop water. There is use of substantial steel work in order to extend the and close the scrubber structure. And also from that it comes a vision of the ship, and new calculations need to be done with regards to the vessel stability and statutory approval. And there is a possibility that due to the increase of weight, that the vessel will need to have, according to the rules, and possibly will need to do planning experiment and increasing the cost. And also the added weight is also reducing the dead weight of the vessel. So we can see that here for a case study that from this organization called Green Ship for a 38,000 deadweight tanker, about the installation of a scrubber system. We see that the estimated cost was about $6 million, which is a substantial cost for retrofitting such a vessel. And also in the graph here, you can see that how the scrubber dimensions are changing according to the engine output. So this means that for vessels with a big engine output, that the would be very large. Even for small vessels, the systems will be for them to carry. So this is something that is a big disadvantage in the scrubber technology, and will in the future for this technology to be sustainable. Now we move on to retrofitting with LNG. The retrofitting with LNG has some prerequisites, and of course it needs to have a main engine conversion, which is a very subtle work, and also an LNG inert gas system needs to be installed. We need the auxiliary gas systems. Of course, we need to install the LNG storage tanks on board, probably somewhere out of in the outer space of the vessel on the open deck, as you can see also in here. Then you need a new fuel supply system. You need to remove the existing pipe to reconstruct piping delivery from the fuel engines. Also construct foundations for the storage tanks, and in general a lot of steel work. Again, you need to have a light ship revision and do possibly have a lot of statutory work in order for the vessel to comply with the changes with the regulations after the changes it has. So again, we have this result of a tanker sample where quotations were given for such a retrofit, and we can see that that goes up to $7.5 million to do such a retrofit, which is of course a bit higher than with scrubbers, but if we take into consideration the gains that we might get from lower LNG fuel price, it could possibly make more sense than retrofitting with the scrubber. Other problems with for retrofitting with LNG, we have few bunkering stations, and the network is not as dense as oil bunkering. So this means that bunkering, LNG bunkering infrastructure, and even bunkering vessels do not exist. LNG bunkering vessels will be a major challenge for the future. You can see in the map different bunkering hubs, mainly for oil, and also there are some LNG export and import infrastructures. However, dedicated infrastructures for LNG bunkering of ships at the moment are very rare. But there are developments in mainly Northern Europe of new infrastructure, and gaining pace for the next years. So lastly, we come to the Ballast Water Convention. This is another measure in order to prevent minimize the effects of ships in the environment. And this is coming forward with firstly the ballast water management plan, which should be on board vessels, should have a plan in order to show the sequence of changing ballast without discharging, let's say, alien species to other waters. And also there's the ballast water treatment, which has come with a time schedule for all ships to comply after some prescribed time. So as a consequence of this convention, there have come up many manufacturers with different solution systems, and they use different technologies. Just some common are UV or electrolysis, or combination of UV and pre-filters, or even electrolysis and pre-filters, and also some technologies that they are under development. A big problem with is that the sampling procedure is at the moment prescribed, but it's not yet very solid in how it can be neutralized for all vessels and for all ports and all conditions. So you can see the manufacturers by country of origin. Most of the manufacturers are from South Korea. They're following by Norway, and then also we have substantial manufacturers from China, and also a lot of type approving administrators or class, and which are mainly leading Norway and also DNV from Norway. For retrofitting for ballast water treatment requires a lot of onboard work. Firstly, they need to have an arrangement of the plan. There have to be done drawings and coordination. There is a lot of piping involved, and also steel work in order to install the ballast water treatment unit within confined spaces of existing vessels. And also various calculations of the capacities, ballast capacities, and also electrical load balance of the vessels in order to handle the unit. And finally, all this have been done need to have a plan approval procedure in order to come to the class and be approved for final construction and fitting. So it is estimated that there is a very big number of vessels which are required to install the ballast water treatment, and currently there is a wonder on how these vessels, how so many vessels can be equipped in actually less than a decade. And we can see the trade here in the graph, and you can see that the numbers, because after 2016, most of the vessels will start to be in force for ballast water treatment installation after 2016. So you can see a very big increase in existing vessels retrofitting from 2017 to 2019, and this means that operators, manufacturers, and also class societies, they are already preparing for it, and most of them are even retrofitting before the actual date of needed compliance. So to conclude, expectations for the retrofitting market by 2020, 2030. Well, hopefully the economy will recover with starting a new shipping and shipbuilding prices, also taking into account the pressure from such regulations that will put ship owners into thoughts of buying new ships rather than retrofitting the older ones. Economies of scale and widespread use of LNG will reduce the equipment cost at the moment, which is a very substantial cost of retrofitting for LNG is the actual equipment of the LNG. Probably the technology advancements will reduce the size and the cost of scrubbers. And there will be time until then to solve all the technical pending issues and possibly to train an adequate number of skilled seafarers to operate the new technologies installed on board the ships. Intelligent financing is needed for eco-retrofitting. Operators will need to find the liquidity and the financial incentives to actually go for retrofitting jobs. And also there is a potential of positive cash flows from carbon credits, which is something that we don't know yet if it will be implemented, but there are of course discussions and thoughts of implementing a carbon market within shipping, similarly as in aerospace industry. So thank you for your attention, and thank you. This is the last lecture for today.
Are there any questions, please? No, sorry for the technical problems today. It was a strange situation. I hope that you were able to follow the lectures. We will continue tomorrow with our next speaker. Thank you very much for attending today. Have a nice evening. Sorry. Μόλις τους έβγαλα όλους έξω. Άργησε.